This question comes from a user who asks, what if you had a camera that could actually enhance forever, zooming in past atoms and into the quantum foam? In police procedurals, enhancing a grainy security feed is a money-summoning magic spell used to find a killer. In reality, as any Hubble operator will tell you, the fundamental problem is that resolution has hard limits. To start, we have to define our zoom. Our best visible light telescope, the Hubble, has limits that turn Pluto into a mysterious blur. To see a normal desk, Hubble would have to overcome motion blur. At its orbital speed of 7 kilometers per second, the desk is speeding by too fast to catch a clear frame. But let's assume you have a custom system that eliminates blur. You zoom past the desk, past the wood fibers, and hit the atomic level. This is where we run into a horrible idea. To see an object, you have to bounce a photon off it. To see something as small as an atom, you need light with a wavelength smaller than the atom itself. This means you're no longer using visible light, you're using X-rays and gamma rays. As you enhance further, your camera's flash becomes a weapon. In the scenario where we focus the sun's output into a 1-meter beam, the air turns into a plasma that dumps heat as a flood of X-rays. By the time you're zooming in on a single carbon nucleus, your camera is delivering so much energy that your subject will stop being biology and start being physics. If you were trying to photograph a person at this level, the incendiary twilight of your camera's flash would wrap around them, vaporizing everything in sight. Like a relativistic baseball hitting the air, the atomic nuclei in the air molecules would actually fuse with the nuclei of your subject, creating an expanding bubble of incandescent plasma. But the question says forever. To reach the quantum foam, you have to zoom past the nucleus and into the Planck scale. This is a highly theoretical realm where we hit the limits of even string theorists. At this scale, the energy required to see anything is so high that the energy itself begins to warp space and time. According to Dr. Keeler, a string theorist, once you have energy per particle over the Planck scale, you're not just taking a photo, you're potentially creating a black hole. If your camera successfully enhanced the quantum foam, it would concentrate a universe mass worth of energy into a space the size of a grain of fine to medium fine sand. This black hole would pass right through any sieve, and while it might be low profile due to its tiny size, the accretion disk formed by it eating your camera would let off a tremendous blast of radiation. In the end, your quest for a perfect close-up results in a sizable crater centered a few hundred feet behind where you were standing. The reflected light from your quantum foam flash would be 4,000 times brighter than the noonday sun, likely scouring the face of the Earth clean. On the plus side, since the sun would be drowned out by your camera's radiation, you would briefly have better astronomy without atmospheric noise, at least until you were vaporized by the shock wave.